Greetings from Bonn. Greetings from Bonn to wherever you listen to us. My name is Atina Trakas, and I'm here with my colleague Esperanza Cuartero, supported by our very pressure colleagues from Comply Trust IT, Sara Wotzi. And yeah, we'll welcome you to the midterm webinars of Code for Earth. And before I say a few words about Code for Earth and who will be presenting, I give the word to Sara for some logistics.
Okay, hi everyone. This is Sara. Just a very quick thing. This webinar is being recorded. It will be available on our YouTube channel and our social media as usual very, very soon after the webinar. And if you have any questions for our panelists, please do not hesitate to write them in the Q&A section. You can see that at the bottom of your Zoom. And just write your answer, like your questions there. We will answer them at the end of the webinar so that we can have a smoother experience for everybody. Thank you so much and enjoy the webinar.
Thank you, Sara. Good. So some quick facts and background to Code for Earth. Code for Earth is a key innovation actions run by ECMWF, the European Center for Medium Range Weather Forecast, and supported by Copernicus, Destination Earth, and partner organizations. And the program addresses mentor-identified challenges in our entire community, Earth science as a broader community, but then focus on weather, climate, and atmosphere. Each summer, we welcome selected individuals or developer teams who send in applications on the challenges, proposals how to solve the challenges. And all the colleagues or all the participants have different background. So you will see computer scientists, AI experts, as software developers. And the entire program is all about innovation, collaboration, and open source software development. And the selected teams that successfully complete the projects by the end of August, they also will receive a 5,000 euro stipend. And today we hear from 5 of the selected projects and project teams where they are, what are the findings so far. We hear about their projects and maybe already some first demonstrators. And please keep in mind, this is the midterm, so we have still 2 months for coding. So here you can see the timeline of the program. So we started in February with the call for participation. And then in April, we did the selection. So we evaluated all the proposals we received, and the mentors evaluated the proposals and selected for each of the challenge a team. And we entered the coding phase with 11 teams. And since May, they are working with their mentors to solve the challenge and to work on their projects. So this is where are we now. And I mentioned that we have partner organizations, and here a big thank you to our joint challenge partners. That's NSOE, as well as Forschungszentrum Jülich in collaboration with CSOC. Then we have Helmholtz-Zentrum Herion. A big thank you for you as well. And IFAP, the International Foundation on Big Data and Artificial Intelligence. And both Helmholtz and IFAP, Helmholtz-Zentrum Herion and IFAP, were supporters already or challenge partners already last year. And we're really happy to have you with us also in this edition. And with that, I would like to hand over to my colleague Esperanza, who will say a few words.
Hello, good afternoon, everyone. And on the screen, you can see the mentors who are helping the Code for Earth teams this year. We have in total 42 mentors, external and internal mentors. And we would like to take this opportunity to thank all of them for their continuous support. Yes, next slide, please. Yeah, and here is the agenda for today. As Tina says, we have invited 5 teams, 5 Codeware teams, will present, introduce their projects and also the progress so far. Their teams presented today or the projects are Visualizing CAMS data in the browser, EarthReach, Open Data VISIO, Fire Front Radar, and PolyShell. Next slide, please. Yeah, the second webinar will happen on 24th of July. So you save the date and you can join us for if you are curious about the 6 remaining Codeware teams will present their projects too. But now, without any further delay, we welcome the teams presented today. And we have the first one on the spotlight is Visualizing CAMS data in the browser. The developer behind this project is Joachim Konislip. He is developing, he's creating a tool to make air quality forecasts more visible and easier to explore. So the floor is yours, Joachim, when you're ready, tell us everything about your project.
All right, hello. My name is Joachim, and yeah, I'm here to present this project about visualizing CAMS data in the browser. So let's begin. First of all, let's start out. It is actually possible to do this, and I think a good start is actually just to show it as a demo before we really get into the details of why it's interesting or what it improves on kind of the current state of the art. So let me see if I can get this thing to go away. So this is actually a local demo running that shows a bit about what you can do. And so right now we are looking at some black carbon aerosols here. And because we have the data actually in the browser, it means we can do a lot of cool stuff because we have it so locally. So for example, we can have, instead of showing the grid cells, so obviously we can add some smoothing. So they are a bit smoothed, right? And we can also do the same for, instead of doing it spatially, we could do it in the color space so that the colors are now smoothly interpolated by the values. And we can sort of keep going with this. So we have the time steps that we can go through here and step through. But we can also mix between the time steps, linearly mix it. So maybe it's a bit subtle. We can, if we close off the smoothing, we can see that we can actually get some very small changes in the forecast between hour 3 and hour 2, or hours 3 and 4. And because we can do this, we can also animate between them. So we have a little button here that we can animate. Now we get like a smooth movie stepping through the forecasts. And this is actually quite general. It works for many different sorts of fields we can find in the CAMS data set. So we have, for example, this is the ozone field, and yeah, we can show all kinds of stuff. And it's actually so general that we figured out that we might as well try to do it on other data sets, not just CAMS. So for example, we can go to error 5, and we can also see some error 5 data. This is a very big data set. So it's many, many hours. It goes back to the 50s, I think. So this is kind of the current state of the project. And I'll go back to my presentation, and we can discuss a bit about why we're doing this. So the current solution we have here is that we have these static web maps, and they are produced in a static way on a server. So they're kind of far away, the data is far away from the user. And this means that they are way less interactive. So you can see before I could pan and zoom and change the color maps and do all of this stuff. Because the data is so far away on a server, we basically have to create a static map and show that. So this improves the current situation by adding lots of interactivity for the user. There is some downsides, of course. Maybe this will actually require way more bandwidth, but maybe that is okay in today's day and age with the way we have internet architecture set up. So how is this actually possible? This is sort of a little bit of a background without going into way too much detail. So the way it works is to even make it possible, we store these files in this new modern data format called SAR. And SAR is really efficient for splitting the data up into smaller chunks. And we can store them in some very off-the-shelf technology called S3, which is like all the big cloud providers like Google and Amazon, they provide this as a service, and it's really, really efficient for streaming in blobs of data. And in this case, this is like slices of the data sets. So in the CAMs, it could be a slice in the spatial domain, right? So one time step could be one slice, and it's really easy to fetch these blocks, and it's really efficient, and you can do it in parallel reads, and yeah, it works really well. And then to actually get something rendered on the screen, we actually render this with the GPU, which is why we can have it sort of so fast to animate between and do all of these sort of expensive interpolations. We do it on the GPU, and it's very difficult to write code for GPUs. So we use this DeckGL abstraction, which really, really helps to make all of this mapping and putting it on top of the map and interpolating, makes it way easier to write the shader code needed. And then we just keep stacking it up, and then we have some React app for managing the state, like what's selected, which timestamp is selected, and that's like also off-the-shelf web technology, very modern and well tested, and it's very, yeah, everybody knows how a React app works in the web development business. So this is sort of stacking all the way from the very technical SAR to the very modern off-the-shelf front-end code, which is a very nice framework to work in my opinion. And I think we're already quite far in the project with some good results, but we're going to explore in the future how this dataset agnostic solution could work. I showed this very quick Era 5 demo, but yeah, maybe I'm cheating a bit because it's the producers of these datasets are actually the same. So everything is formatted in a very specific way that's neat for me to use. And we have some problems for very large datasets, even larger than the ones we're using, especially with the spatial resolution. So we're going to employ some tricks there to make it better. And potentially look into if we can do other sources of data for like weather forecasts, operational weather forecasts, or even satellite datasets. So that's the current status and a bit of what we're going to do in the future. And I think I'm a bit early, so hopefully that's okay. I'm going to give it up for the next person.
Thank you very much, Joaquin. Impressive demo. It not only works for CAMS data, only for Era 5, so
Yes.
or any or even weather forecast data. Very
potentially. I think if everything is in place, it will work. Right?
It's still the second half of the coding phase, so to investigate.
Yes.
Thank you very much. And now we present the second project is in this session is the project is EarthReach agent, and the developer behind this is Romain Beza. Welcome, Romain, and you are going to present your project, which is it's about using two artificial intelligence models to make charts accessible to experts and scientists who are visually impaired. So tell us more about your project, please. When you are ready, I hand over to you.
Thanks a lot. So hi everyone, I'm Romain. I'm developing EarthReach. So indeed, this is a dual large language model agent framework to generate validated weather charts descriptions. So imagine that you're a blind scientist working in the field of earth science. You may know that a lot of the important communication around the results, the interpretation and all that, this is made through charts and a lot of visuals, like the map on the right. So imagine that just like that, it is blurred. You have access to almost no information on this visual data. So you are really left aside of all the improvements in the field, all of the potential use that you could make of this information. You cannot convey them, you cannot analyze them. So you cannot contribute to the field, essentially. Of course, that's a critical problem that we are trying to alleviate in this project. And this is motivated by the fact that there is no convincing scientific alt text generation solutions out there that already solve this problem. So essentially, our goal is to generate insightful, accurate, and accessible description of weather forecasting charts for blind or low vision people in order for them to contribute equally to the field of earth science, just like any other scientist. So let's dive into the heart of the matter. What have we achieved until now? This is a concrete example. On the left, you see a weather chart that has been generated with the EarthKit plot. It's a visualization library. You see it's centered around Western Europe, maybe even more so France. And it shows two types of variables. There is the 2-meter temperature and mean sea level pressure. And this is occurring at the end of April. On the right is the description that was generated by the system. So you see, first of all, that it's very long and very detailed. It starts with some kind of overview of the contextual information, where it's located, when is it, these things. It also describes each variable, temperature and pressure independently. And if we continue, because yeah, the description goes on the right, you see that this is the end of the description. So when it has described the variables, it will try to interpret them and extract the meaning of the chart, if any. So some of the characteristics of this description that we're able to generate right now are that they do have a coherent structure and somewhat of a logical flow. They use precise and accessible scientific language, meaning that we do use the terminology of the field, which is important for efficient communication. And also, we try to make them accessible, meaning that we don't refer to visual elements, such as, for instance, if I were to say, okay, it's hotter around the red region. All right, where is the red region? I'm a blind or low vision, so it doesn't really help. So we avoid these kind of errors in our descriptions. It also targets relevant data because, of course, in this type of visuals, you have so many information available. You can have to filter which ones you really need, you really value. And when you have decided what are the important information, you of course need to make them accurate. You don't want to be wrong when you convey some kind of data or interpretation. However, you might note that if you had time to read the description, I doubt that a bit, but still, it missed an important piece of information, of context, is that if we go back to the image, you see that it's very hot. It's spread out throughout Western Europe. And for the end of April, this is super hot, and that's uncommon. And typically this day was labeled as a heat wave, and this doesn't appear in the description. We do know there is some kind of gradient. We do know there is some kind of movement, and we do know it's hot, but it does not be labeled as a hot wave. So it still misses some kind of seasonal context that we have to work on in a next iteration. So we've seen this example, but is it any good? We have asked some experts, Earth scientists, to guide us into what should be a good description in terms of pure language quality, but also structure, type of information we want to extract. And we have created 4 quality criteria. This is not out of nowhere. This is also using the current state-of-the-art in large language model evaluation. And these 4 criteria are these ones. So there is coherence, fluency, consistency, and relevance. Each of these scores can be put on a scale from 0 to 5, 0 being the worst and 5 being the best score. And I'll come to that a little later, but we have created an evaluator system that is capable of automatically grading our descriptions. And this will have its importance, but if we look at the table on the right, we see in these preliminary results that our system is better than out-of-the-box large language models, such as Claude 4, because all of the scores are better for our system than the baseline one, essentially. So how are we doing this? This is a high-level schema drawing of the system. As I was saying earlier, it consists of 2 large language models interacting with each other. I use the term agent because they are enhanced with some tool use, some specific techniques and orchestration. So it's not just we ask a large language model to generate something. There is a lot of engineering going on around them. But basically, the flow is that the generator agent takes in a weather chart, extracted metadata from the weather chart, as well as full access to the underlying data that was used to generate the chart. And it will generate a first draft, a first try of the description. We have a second large language model that analyzes the description according to the criteria I described earlier that were developed with expert scientists, and it will score the description. It will also provide reasoning steps and feedback to the generator. The generator will then analyze this feedback and try a second time or a third time or a fourth time to generate a better description until the criteria, the scores are reaching a point that is high enough above a certain predetermined threshold. And of course, there is a lot of guardrails that I won't dive into. It also implies a lot of data engineering and prompt engineering, sorry, a lot of things. But basically, this is the idea. When we have had a few iterations of this flow, then we have our final description, essentially. So now what's next? So large language models are very hard to evaluate. They are not very reliable systems. So the step that we're undertaking at the moment is creating a user study that will have for objective to evaluate the accuracy and the quality of our descriptions as generated by our generator, but at the same time also see if our evaluator correlates well with humans' judgment of quality. And this will allow us to have some confidence in our results, but also to drive continuous improvements because we will gather a lot of qualitative and quantitative feedback that will essentially tell us what's important and what's not and what we should focus on. And finally, we will integrate the EarthReach system into EarthKit-Plot, the visualization library I told you before, simply to make the charts generated by this library accessible. Because with just a simple API call, you'll be able to generate alt text descriptions that you will be able to include in all your publications or your website or things like that. So that's the gist of the system as of now. Thank you.
Thank you very much, Roman. Very good. Very useful. Will be very useful. So, if any of you have questions to Roman or to Joachim or to the rest of the teams, please you can type the question in the chat, and we will have a session, a question of questions and answers at the end of the presentations. So it's time to welcome the third team. The project is titled Open Data VISIO, and the person behind is Alenka Senica. Welcome. She is creating a Jupyter notebook to manage access and download real-time data, ECMWF real-time data. So please, the floor is yours, and you're ready.
Thank you, Esperanza. Can you see my screen?
Yes.
Okay, perfect. So I will present you the one-stop shop Open Data VISIO, which will provide you with tools to explore ECMWF open data as well as guidance. ECMWF is transitioning to a fully open data policy, making its weather forecast data more accessible to various sectors. This includes data from both the integrated forecasting system and the artificial intelligence forecasting system. The move aims to facilitate wider use of high-quality numerical weather prediction products across diverse fields, aligning with broader global trends and initiatives promoting open access to meteorological information. The data is provided at the highest available resolution. They are released under a Creative Commons Attribution 4 international license, allowing for commercial and non-commercial use with proper attribution. Data is available soon after its production, with some datasets released with minimal delay. How ECMWF open data impacts different sectors. On disaster risk reduction, open data allows for better preparation and response to extreme weather events, supporting initiatives like early warnings for all. To ensure universal protection from hazardous hydrometeorological, climatological, and related environmental events through life-saving hazard early warning systems and resilience efforts. On research and development, researchers across various disciplines and operational meteorologists can leverage the data for studies in meteorology, climate science, and other related fields. On agriculture, farmers can utilize weather forecasts to optimize planting and harvesting schedules, manage resources, and mitigate risk associated with extreme weather. On renewable energy, open data on wind and solar resources can be used to optimize the placement and operation of renewable energy infrastructure. On public health, weather information can be used to predict and prepare for heat waves, cold spells, and other weather-related health risks. On education and awareness, open data can be used to educate the public about weather and climate, promoting greater awareness and understanding. On finance and insurance, weather forecasts can be incorporated into risk assessment models for weather-dependent industries. On transportation, open data can aid in planning and managing transportation networks, minimizing disruptions caused by adverse weather. Pilots and airlines especially can use accurate weather information for flight planning and safety. Open data are available from the following locations: ECMWF data store offers datasets from today and up to 4 days ago. Data can be retrieved in different ways using Python packages, wget, and curl. Amazon's AWS S3 buckets host data from 2023 until now. And it's important to bear in mind the file naming convention when a user wants to download historical data. To give one example, products produced at 0.4 degrees were retired at the beginning of this year. Now the 0.25 degree resolution data are available, which translates to approximately 28 kilometers. Microsoft Planetary Computer makes the ECMWF products available for the previous 30 days. However, Microsoft Azure has changed the anonymous access function to the ECMWF Open Data. One cannot download the data using ECMWF Open Data package because the actual data assets are stored in private Azure Blob storage containers. Alternatively, one can access data using their PyStack client library, and after creating a client, the user can automatically modify the spatio-temporal asset catalogs objects returned by the API and download the data assets. And the last one, OpenVisio, which with an open source weather API, one can access forecast data for up to 16 days or historical data from 2017 onwards. It's possible to choose non-commercial, commercial, or self-hosted license. And it's also important to bear in mind that the user has to specify the exact coordinates and time interval when retrieving data. Meteorological data, especially real-time weather forecast data, arouse considerable interest in many different sectors. And currently there is no all-in-one solution where one could find all the requested information to process ECMWF open data. Therefore, users spend more time to analyze the data. The main objectives of this challenge are to improve findability, accessibility, interoperability, and reusability of ECMWF open data. The evolution of a comprehensive guide will enable the scientific and user communities to have access to the state-of-the-art tools and will assist them to extract relevant information from the vast arrays of forecast data and integrate it into their workflows. For this project, I have used the following tools: Jupyter to create Jupyter Book and Python with EarthReach, ECMWF Open Data, PyStack Client, Planetary Computer, and OpenVisio requests libraries, as well as other packages. The tutorials provide the user with useful tips on efficient data downloading using programmatic methods and other approaches for optimal retrieval of continuously updating real-time data. And what is more, with the main points and lessons learned about what challenges a user can be faced with when analyzing open data. Here is our case study. In the end of April 2025, Western European countries experienced unseasonably warm weather. These plots demonstrate the geopotential height and temperature over Europe from 29 of April to 2nd of May at 500 and 850 hectopascal. Geopotential heights contours indicate that over France was a strong anticyclonic system which lasted several days. When we are faced with blocking highs, this means the same kind of weather for a long period of time, as long as several weeks. We can also experience the prolonged droughts. High pressure systems bring us few or no clouds. Light winds and strong sunshine makes the weather hotter. In the first graph, analysis of 2-meter temperature of the IFS datasets on 30 of April at 12 UTC over France is shown. And one can see the sign of a heat island over Paris and London. When we compare our analysis of the 2-meter temperature of both the IFS and AIFS single data sets, we notice that IFS deterministic model better predicted the event as IFS. The last forecasted lower temperature values over France. Similarly, for the IFS control forecast of the ensemble prediction system products. And next steps in this guide, by the end of coding phase, I will include further examples of different weather situations and best practices in processing and plotting open data, as well as deliver a real-time forecast of selected parameters over a chosen domain using the latest forecast data. Thank you.
Thank you very much, Lenka, for your nice presentation and very, very, very helpful tool for our users, especially from October when all the open datasets, the datasets will be open without information cost. So thank you very much. And now we present the full team is Fire from Radar. We have two speakers here, is Lucy Coley and Marina Capolingua, and they are creating a web application to explore real-time fire. So the floor is yours. Please introduce your project.
Thank you, Esperanza. Hi, everyone. I'm Lucy. As Esperanza said, we're part of Challenge 13, I believe, with my teammates George and Marina. Marina and I are going to present today. So I'll just introduce the first few slides. We'll talk a bit about our objectives, what we've achieved so far, the data that we're using, and the future steps for the next few months. So what is the project? As Esperanza said, we're creating an interactive web application, transforming the ECMWF fire-related products into an interactive and dynamic tool. And the main objectives are on enhancing accessibility, usability, and the impact of these products. We're looking at two main indices, the Fire Occurrence Probability Index, or FOPI, and the Probability of Fire, or the POF, which are both used in wildfire risk assessment and management. And used together, they can provide a comprehensive picture of wildfire status. And the idea of the app is that it's specifically targeting the more science-based audience, so researchers, government agencies, things like that, to allow them to prioritize surveillance, allocate resources, for example, firefighting resources, and also plan mitigating strategies for these events. And so the main objective of the product is just to enhance accessibility for these people specifically and transform complex data sets in a more interactable way. And the reason for this is, as I'm sure you've all seen, thank you, Marina, in the news over the last few years, there have been some significant wildfire events as global temperatures rise and vegetation dries out. The conditions for extreme wildfires are even more common and turning what were once manageable events into major disasters with people being displaced and evacuated. Give me one sec. I just need to take something off the puppy. The noisy toy. Yeah, so into these major disasters with people being displaced. And so our app is based, because the app is using probability indices, we're hoping to provide more insight into foreseeing and effectively planning for such events. I'll just go into a little bit more detail on the two indices. So the Fire Occurrence Probability Index, or FOPI, combines the Canadian Fire Weather Index, or FWI, which is a meteorologically based index used worldwide to estimate fire danger, and it combines it with remote observations of vegetation characteristics to better predict landscape flammability. So it's designed to improve fire danger predictions. And then the POF, or Probability of Fire, provides accurate forecasts of fire activity up to 10 or even up to 30 days in advance, and can also be used to investigate historical shifts in regional fire patterns. And so while some fire indices are based on meteorological forecasts, the POF also uses a model which takes into account vegetation characteristics. So these are the two indices we're looking at and evaluating and hopefully presenting to the user role in an interpretable way. And so I'll hand over to Marina in case she wants to say anything more about the indices and also present how we've gotten so far.
Yes, thank you. I try to share a live demo of what we have reached till now. So during this week, we focus on setting up the architecture and the landing page for our web app. As you can see, the first user interaction is with the global heat map showing the POF values for the current date. And values are equal or above 0.05 can be considered severe condition and are expressed for the darker red color. Using a drop-down menu, the user can choose the different forecasts available for that date, and in this case, for the POF index are 10 days, as you can see here. And using a date picker, so also the user can choose the date and find the relative forecasts associated with that date. On the left side of our dashboard, we can find the drawing tools where the user can select a specific area of interest. And in this way, have a better evaluation of the situation for the specific area. With this download button, there is a chance for the user to download the heat map of the area to save it locally. If you want to see the data about the FOPI, we can use this toggle button at the top right corner. And we just need to wait a bit, but at the end, the new data are loaded. And in this case, we can find even the same forecast for this index that are at an interval of 3 hours for 10 days. This is where we arrive today at this point, but now we can talk a bit about the infrastructure that we have used. And we built this interactive dashboard using TypeScript language and the React library for the front end with the leaflet to render the heat map. To render the maps, and we use Maintain UE library for the user interface components. The heat maps are generated from the backend system, and the backend is built primarily in Python with Python language, and we use Fast API to provide the data. The data are at the starting point as a netcdf file, but we transform them with in a ZAR format to enable efficient chunked and cloud-friendly data storage and retrieval. Our next aim for the future month is to enrich this initial map with a suite of tools designed to support decision-making across different time scales, from short-term fire response and long-term risk planning. Forecast comparisons and other frequency charts will help users to monitor evolving fire risk on daily basis. Time series plot and historical event playback can provide the context by linking past forecast condition with the actual situation. And finally, charts focused on biomes, vegetation types, and administrative zone will allow users to tailor insight to their specific geographic or operation needs. thank you all of you for listening, and to ECMWF for this chance.
Thank you very much to you. Very impressive. The demo, the global, unfortunately, is very red, but it will be very useful, your web application, for sure. And now the last but not the least team is PolyShell. PolyShell is formed by 4 team members: Niall Oswald, Kenneth Martin, Miriam North Ridow, and Joe Wei Tam. But now I think it's Niall who is going to present PolyShell. PolyShell is about solving a problem. It's related to complex shapes of data. You will talk about it, and we learn what this really means, PolyShell. Please, Niall, the floor is yours.
Okay, so can you see everything?
Yes, you can. You are saying.
Okay, perfect. So thank you for the introduction. As you said, I'm Niall. I'm also here with Wayne, and we're PhD students from the Mathematics for Future Climate Centre for Doctoral Training at Imperial College. Sadly, our other 2 teammates couldn't make it today, but we'll persevere through. So the project we're working on is called PolyShell, and we're working to develop a new polygon reduction algorithm. So in other words, an algorithm which can take a polygon and approximate its shape using a fewer number of vertices. So the reason why ECMWF is interested in this in the first place is that they're currently developing a data extraction service called Polytope, which allows users to query high-dimensional data using polytopes as query objects. So the current algorithm scales well for high-dimensional shapes, but it really struggles with highly detailed and complex 2D polygons. So conventional polygon reduction algorithms cannot be used in this case because Polytope wants to guarantee its users that within the query region, all of the data is returned. So while many polygon reduction algorithms already exist, there are none which we're aware of that can consistently over-approximate the original area.
Sorry, Niall, I don't know if you are advancing the slide.
No, I'm not yet. I will be now.
Sorry about that.
Okay, so that works.
Yes, works.
Okay, great. Yeah, so in other words, we're working to develop an algorithm which can reduce an input polygon while ensuring the simplified polygon can completely encompass the original area. So as our project is intended to be used to resolve an inefficiency for polygons with a large number of vertices, we need the algorithm to be as efficient as possible. So we're currently benchmarking with polygons on the order of tens of thousands of vertices. But if we can make the algorithm work for even larger polygons, that would be great as well. So it's not enough to just simply over-approximate the original area. We want a good approximation. Otherwise, we'd just end up using the convex hull. But what we mean by accuracy is quite subjective. It's quite hard to define. So do we just measure the difference in the area of the 2 shapes? Or do we want to retain certain features in the polygon, like rivers, which are quite small? So as a result, we need a kind of a user-facing parameter which can be tuned to satisfy the user's tolerance for the error, but potentially maybe use other algorithms as well, which can treat geometries differently. So before I introduce the algorithm, I'm just going to describe a quick reduction that we can do, like under these requirements that we stated. So starting with the input polygon, we can first compute the convex hull of its vertices. And because the points are ordered, we can use a faster algorithm for this. If you're interested, we can do it in linear time. And this construction allows us to identify the vertices which are irremovable. So in other words, the loss of any vertex in the convex hull will mean the reduced polygon no longer encompasses the original shape. So now that we've identified the fixed points, we can reformulate into this reduced line reduction problem. And here the endpoints of the line string are vertices on the convex hull. Yeah, so once we reduce to this case, it's a lot simpler, and we can just, the idea is to produce a line segment within this white area. I'll lose my train of thought. Yeah, so this is the problem we're effectively reducing to solve. But there's another benefit from doing this, and that's we're able to parallelize the problem. So when we do this, all the line segments completely decouple, and we can solve the problem, as I said, entirely in parallel. So this is kind of as I said before, it's kind of difficult to define what a good reduction is. So this is kind of the sliding scale of how many points we have. Where on the left is the original. We have all of the vertices, all of the detail. And on the right, we have the convex hull. So this is the minimum polygon that we can produce that still covers the original area. And somewhere in between, we want to define an optimum, but there's obviously there's potentially millions of possibilities to choose from. At every point, you have a whole new set of polygons that you could choose. So we want to find an algorithm which can efficiently either find this optimum or just get somewhere close, which is more likely what we're going to do, just because it's too difficult to do in the time constraints. So here's a common algorithm used for line reduction, and it's called Visualising and Wyatt. And the method can be described as follows. So we start by associating a score to each vertex, and this is taken to be the area of the triangle made up with the vertex and its neighbors. We store these in a min heap, which is a self-sorting data structure, and that allows us to remove the smallest element at quite low cost. So once the heap has been constructed, we can iterate over it. And in each iteration, we start by popping the smallest element. This gives us the vertex and its assigned score. If the score is greater than some set tolerance, then we break from the loop. And if not, we continue. And then we remove the point, and we have to update both of its neighbors. And then we continue once the heap is empty or once we hit our break condition. So this algorithm works great for line reduction. And it has quite fast performance. It's only O of n log n. But it doesn't over-approximate the original shape. You can kind of see this on the right, where the red curve is kind of going inwards. So we need to be able to fix that. But it's relatively straightforward, thankfully. And we just need to assign, instead of using the unsigned area, we have to use the signed area for each point. And then if we have an area which is negative in the signed case, then we just skip these points and continue. So we treat them as fixed. And that works great. So we can over-approximate the shape. We have some issues. And it's possible to generate geometries like this where we have self-intersection. So this is like a small channel. The blue is the interior of the polygon. The white is the exterior. So this is like a river going inwards. But you can see if we remove the point at the top, which is for the smallest vertex, we can cross over. We end up with this overlapping region here. So to fix this, we have to do a query. We basically, at every time we remove a point, we have to check if it's valid. And this is quite expensive, but we can use an R tree to speed things up. So that's what we do. So here's kind of the results that we have. I've got the same polygon. It has 50,000 points, and there's just like various levels of zoom going to the right. And we're able to do a 74% reduction in only 30 milliseconds. So we're definitely hitting our performance targets. So the question is very much, is this a good approximation and is it accurate? And qualitatively on the right, it seems pretty good, but I'm going to transfer over to Wayne, and he can talk about maybe some of the data.
Hi, everyone. Hope you can hear me. So the error losses, the error losses for the example that now just showed is plotted against the points that are removed from the polygon. And there are two things to take away from this figure, which is, first of all, each color represents a different concave segment, as mentioned by now earlier, where you decouple everything through the convex hull. And as we mentioned, like through this uncoupling, we can break down the overall problem into independent line segments to reduce them and remove the points independently. And the second point is that the area loss grows exponentially. So you can see that especially towards the end of each line segment, as the algorithm removes the triangle with larger and larger areas, which also kind of validates the implementation of our algorithm. Next slide, please. And currently, our loss function is solely based on the area of the triangles formed by 3 different neighboring points. And these triangles can have very different shapes, but they kind of add up to a very similar error magnitude. So we see this as kind of a potential limitation to our algorithm, because in some cases, the shapes of the triangles might be more important than their areas. Maybe if they better represent the geometrical features like the rivers or the borders of a map of the polygons. So one of the future works is to incorporate new metrics into our algorithm in order to provide the users with a much more robust reduction software. So in conclusion, the features that we currently have retains coverage of the original polygon. It is highly performant, can be done in milliseconds, and we achieve a time complexity of O(n) log n. And as I mentioned earlier, the algorithm does not distinguish the triangles of equal area, so that's what we're going to work on in future. And in terms of parallelization, so currently we are sending each independent light segment to each individual call or thread, and we are investigating further options to parallelize it even further. And we can also add features that are missing. So we can have adaptive resolution, where a certain part of a map or a polygon can be reduced much more than the other parts of a polygon, or we can have parameters to tune our algorithm. And last but not least, we can reduce even further of even the convex regions of the polygon. So these are different directions that we are planning to investigate and explore. Yeah, thank you so much for listening, and open to any questions.
Thank you very much, Nayal and you, Wayne, for your nice presentation. And now it's time for the questions. I hand over, Atina, to you. There are questions. You're muted.
We have a couple of questions. Yeah. We actually have 2. Yeah. We have one for Alenka specifically, and the question is, could you please specify the Python packages utilized in your project, and if it is feasible for users to implement the project using the PyCharm Community Edition by JetBrains?
Okay. Yeah, for this project, I use Jupyter to create Jupyter book, and Python project EarthKit, ECMWF Open Data, PyStack client, and Planetary Computer. These are both from Microsoft. And Open Meteor requests. This is from Open Meteor. And I don't use PyCharm. However, if Jupyter is integrated in it, I guess you can use it to run those notebooks. However, it's also possible to run Jupyter notebooks when you import them in Kaggle or Google Colab or Binder. So there are a lot of different options. Did I answer the question?
I think so.
Okay.
And we have another one for Joe Wayne Tan. So Joe Wayne, could you please clarify why the polygon shape was specifically chosen for the analysis instead of alternatives such as a rectangle, triangle, or an hexagon?
So I'm not sure if I fully understand. I'll try to answer it. So the example that we showed for our analysis is part of the Ionian Sea, which is an actual map of on Earth, and but that's not the only polygon that we are testing with. We have like different test cases for unit testing, and we generate like random polygons as well to test our algorithm. So I'm not sure if it answers the question.
I think I don't know, I don't quite follow as well, but if you're asking about like the triangles where we showed like 6 different triangles of different shape all with the same area, kind of the reason why we're interested in triangles is that's kind of how the algorithm works for Visualising and Wyatt. So like as we said, we kind of assign a score to every single point using the area of the triangle it makes with its neighbors. So kind of the idea being, if we remove this point, how much area are we going to lose? So that's kind of why we're looking at triangles rather than maybe other shapes.
Okay, thank you. I think we do have another question actually. It's a question from Marina actually to Roman. As an input data, do the models evaluate only the image, or is it a subset of pre-processed data, perhaps with the most significant statistics also provided?
I'm not sure I completely got it, but it doesn't use just the image. It also uses metadata that is generated by the EarthKit plot library, as well as the GRIB underlying data. So both the rendered images, metadata, and the actual data. And as per the significant statistics, it's not provided yet, meaning that I was speaking earlier about seasonal context and interpretation. So you could have an area and you know the average temperature over some seasons or a couple of months. And right now, this is not sent to the model. This is one of the foreseen improvements that we can implement.
Okay. Are there any more? Thank you, Roman, for the answer. Are there any more questions? No. Well, then thanks a lot to Joanne, Niall, Lucy, Marina, and Romain, Alenka, Joachim, and all the team members of today's projects. You can here again the phases of Code for Earth. And you see the last phase, that's our final Code for Earth day. And yeah, we totally encourage you to visit or join us online for that day. But before that, we have another midterm webinar on the 24th of July, where you hear the other six teams. And with that, you can find more information on our website. You can find the project. I posted the link in the chat. And I would like to thank everyone, especially the speakers and the teams, but also the audience. And thanks a lot for your questions. And with that, I'd say thank you for joining. Hope it was interesting for you. Stay tuned. We post on LinkedIn and Blue Sky the progress of the teams, respectively the information on the teams. And yeah, looking forward to see you on the 24th and then online also for the 25th of September. Thanks a lot.
Thank you very much.
Yeah.
Thank you.
Bye-bye.
Thanks, everyone.
Thank you,
Bye.
everyone.
Thank you. Bye.